Alright, hi everyone. This is a demonstration video for Lab 3 Group B's speed control of a DC motor. Basically in this demonstration we're just going to go over basically viewing the speed control work. So to begin, you can see our code here. This is how we adjust our speed values for the DC motor. Right now we have it set to 5,000 RPM, which we'll demonstrate in a minute, with our proportional gain equal to 1,093, which is multiplied high, so it's actually about 1 divided by 60, and KD, which is 2,200. Now, these gain values were selected based on the fact that in order to change a PMW value just 1 in the event of the smallest possible error, which is 60 due to the resolution of our RPM. Our RPM resolution is about 60, or is 60 RPM rather. So in order to convert that, we have, if there is 1 error, it is multiplied by 1 over 60. So 60 times 1 over 60 just equals 1, which converts to a PWM value of 1. So it just kind of, that's kind of the thought that went into determining these gain values and how we went about doing that. Now, this is described in a lot better detail in our report, which is available on our wiki page, as well as obviously in the report we submitted. So if you'd like to learn more about that, just you can visit it on there. So let's try this out here at 5,000 RPM. Download with these gain values. We can just download this to the basic stamp right now, as you can see. Loads the debug window. We can close it here and move on to our stamp plot. This is a previously recorded one. So we restart it here. Now there's a 5-second delay just to give us time to switch over to the stamp plot before it starts running. So you can see the initial jump there. And remember, our goal was 5,000 RPM, so slowly reaching it there. And as you can see, it's leveling off at about 5,000 RPM. So you're noticing some fluctuations right now. The system is stable, and that's not really oscillating. It's meant to be like at its steady state right now. It's just that the resolution of our tachometer kind of limits the ability of our controller. So our controller's doing what it's supposed to. It's just that due to the restrictions of our tachometer, being that it only has 1 cycle per revolution and 60 RPM overall resolution, we're going to get small fluctuations no matter what we do. But the point is that it's it's demonstrating what we need it to demonstrate. So, and actually the reason for that 60 RPM resolution is due to the fact that we tried higher resolution encoders, but for some reason we were getting pulses merging into each other, so we were missing a lot of pulses in our count command. So we decided to kind of simplify our whole design of the thing by just using a 1-cycle encoder. This also kind of limited our controller design in that we wanted our controller to just simply perform the task and be able to be adjustable, but the main thing is that it achieves this 5,000 RPM value, as you're seeing here. So let's have a bit of fun here with it and go on to change the set speed here to let's just say 4,500 RPM, and leave the gain values the same. So we expect a similar response, just it'll go up to 4,500 RPM as opposed to what was done last time. Actually, I forgot to, oh, I did disconnect, sorry. Alright, so let's give it a shot here. Download it to the basic stamp. Okay, so shuts everything off there. Close it. Run over here to our basic stamp and connect. So again, that 5-second pause, and in a minute you'll see it run up to 4,500 RPM. Now this time, because our set point's a little different, we did get a bit of a different response in that. Looks like there's maybe a bit of overshoot there, or maybe it ran right up to 4,500 RPM. But again, we're achieving the results we want in that it's stabilizing at about 4,500 RPM. Again, those fluctuations are just due to tachometer resolution. It's not oscillating. It's just due to the resolution of our system. So as a simple test here, actually, I'd like to just, you're not going to be able to see it in this video, but I'm going to, in a minute, block the sensor, the optoreflective sensor. And by doing that, it's going to give it a 0 count. So the controller will see a 0 count on the RPM, and it'll jack up its PWM value to maximum. So I'll just do that now. So as you can see, we're down at 0 RPM right now. But I'm not sure if you can hear it, but the fan's going nuts. So we let go of it. It'll be up in the air, and then it'll slowly oscillate back down to the 4,500 RPM to our controller. Also, I'd like to test. I'm kind of stopping the fan right now with my finger. As you can see, it's jumping up. And now let go, and it'll come back down. So just a few simple abstraction tests to see that the controller, in fact, compensates for external conditions outside, which is kind of the advantage of a closed-loop system, as discussed in our report. With an open-loop system, assuming there's no discontinuities in terms of energy in the system, like someone stopping the fan or something